Dr. Nakamura. Now I'd like to invite our second speaker, Dr. Christian Ng from Extron, Vice President of Greater China. He will speak about the productivity and performance factors in compound semiconductor production. Dr. Geng has extensive research experience in MOCVD growth, and he has published articles in over 80 publications. 下面有请我们的第二位讲者，爱市场大中华区副总裁傅申根博士。他演讲的主题是 MOCVD 量产复合半导体的生产力与效能关键因素。傅申根博士在 MOCVD 成长研究经验丰富，至今已出版了超过80篇以上有关3、5组半导体的文章。让我们欢迎傅申根博士。Let's welcome Dr. Fu Shenggen.
Thank you very much for the introduction. And I think we have a security alert. Okay. Again, thank you very much. I'd like to talk about productivity and performance, and this is related to MOCVD. And today I will split my presentation into two sections. The first one, I'm going to share with you my view on the market, the LED market, long term, not what's happening right now, and what the market needs are. And in the second section, I will show you how Extron addresses these market needs. And that will be in particular with respect to reactor capacity and wafer size, but also yield and automation. So let me start with the market view. This diagram shows Extron's revenue over the last about 12 years. And I'm showing you this because somehow it represents the number of reactors that we have delivered to our customers. And since the company was founded, it took about 20 years until in 2007 we installed the 1000th MOCVD system. Only 4 years later, in 2011, we delivered the 2000th MOCVD system. So the message is the market is growing much quicker recently. So much more capacities are being delivered to our customers in recent years. And I'd like to show you where these capacities are going. Historically, this diagram I borrowed from Strategies Unlimited, and it shows the revenue by application over time. And it's basically a forecast, but it also shows some historical data here. And the largest market has been for many years the application of for mobile devices like mobile phones, PDAs, smartphones, and it is a pretty big market. But around 2010, 2011, it had been surpassed by another big market. That's the market for backlighting of televisions and monitors. And it is a big market, but we can see it's going to saturate as well. Now, the strongest growing market, however, is the lighting market. It is still small, but it's growing at a very high rate, and it has the potential to grow much bigger than any other application. And how big that is, I've borrowed another slide. This was published by Philips Lighting back in 2009 already, and it shows the lamps market over time, and we can see that it's predicted by 2020 maybe around 90% by revenue will be accounted for LED lighting. So I said it is actually a lamp market, but since these lamps will be fed with LED chips, it is reasonable to assume that the LED chip market will grow with the LED lamp market fairly parallel. So I'm going to superimpose the previous diagram or data onto this one, and we can see it's fairly consistent how the markets grow. and we expect that by 2020 the lighting market, LED chip lighting market, to be about 14 times bigger than in 2010. Now, something needs to happen for this to come true, and that is the costs need to go down. And for this view, I'm going to show you my third and last borrowed slide. This one comes from the US Department of Energy, and it's a roadmap on how the cost should come down from 2010 to 2020, same period. And it is predicted, the cost is predicted to go down to about 1/12. And the epitaxy part, which is this block in this cost, it should be going down to about 1/8. And this is where we need to be helping our customers, the LED chip manufacturers. And now we take a look at the cost breakdown of an LED epi wafer, and we have here the capital cost, the chemical cost, the consumable cost, and those together, they are basically the reactor-dependent costs, and they make up about 90% of the cost of an epi wafer. The rest is labor and fab. That's about 10%, and that is more related to the platform. So if you want to address these reactor-dependent costs, the most relevant part is actually the reactor capacity and the wafer size. And yield is another important subject because it's a multiplier onto the whole cost of ownership. And finally, automation, even though it only addresses the 10% here, it is important because it takes out the human factor in the production. So these three subjects, reactor capacity and wafer size, yield and automation, are now the subjects for the technical part of my presentation. Over the years, the reactor that us and our competitors have offered and delivered to the customers have become bigger. We can see here 6x2, 11x2, 24, 42, and 56, and even 69 2-inch wafer capacities per reactor. But not only the reactors have gotten bigger, also they're geared for larger and larger wafer sizes. So actually, when originally the reactors were designed for 2-inch wafers, back in 2003 we already offered a 4-inch wafer capable reactor, which at the time was operated with 2-inch wafers in these pockets, but now most of those reactors have been retrofitted to hold 8 4-inch wafers. In 2006, we already offered a 6-inch system. At the time, nobody was using 6-inch. Today, it's coming. Today, some customers are starting to use 6-inch. And the latest product is actually already capable of holding 8-inch wafers. So it's always one step ahead. And let me show you some pictures of the reactors. For example, here we see the Cryas 2L showerhead reactor. It can hold 69 2-inch wafers or 16 by 4-inch, and also 7 by 6-inch or 3 by 8-inch. The other platform, the planetary reactor, we can see here 56 by 2-inch and also 8 times 6-inch, and this is a nice example on this reactor is actually the same reactor for 2 and 6-inch. All you need to do is exchange these satellites to hold different wafers. I think you call them Panzer, right? Okay, here we see 11 by 4-inch and already 5 times 8-inch today in use for non-LED applications, mainly for gallium nitride and silicon electronic devices. Okay, now what is the advantage of larger wafers? It may seem obvious. Silicon industry is using larger and larger wafers for obvious reasons, but let me share a view with you anyway. I have here want to show you the impact of the larger wafers on the cost of ownership. And as a start, I'm going to show you moving from 56 times 2 inch to 14 by 4 inch planetary reactor. So the capacity of the reactor is number of wafers times pi r squared. Very simple. If you do the math here for 56 times 2 inch and for 14 by 4 inch, you can see that the area ratio is exactly the same. So the two configurations have the same capacity. However, every wafer has an edge, a wafer edge that cannot be used. So we should actually be subtracting this wafer edge from the radius. If we do so and compare the capacities again, we see that actually the 4 inch configuration has already a 14% capacity advantage over the 2 inch. And if the system cost is exactly the same, you have a larger capacity by 14%. So obviously the costs go down to about 88%. In the running cost, you need the same consumables, the same amount of chemicals, so the running cost also goes down to about 88%. For the chip process, I'm making a very, very simple assumption because I'm an epi guy, not a chip process guy. So I'm just assuming it takes about 50% longer to process a 4 inch wafer compared to a 2 inch wafer. So I have the area of a 4 inch wafer with 50% drawback compared to the area of a 2 inch wafer, and we can see we have a 2.7 times higher throughput just by moving to 4 inch. We can do the same analysis when we go from 56 times 2 inch to 8 times 6 inch. So we calculate the area, and we can see in the area ratio we already have a 30% advantage. Where does this 30% come from? Well, if we go back here on this picture, you can see the spaces between the wafers here. That's the 30% when you move from the 2 inch to the 4 inch. So we already get a 30% advantage, and if we include or take into account the edge exclusion of 3 millimeters, then we're already at 50% advantage. That directly translates into investment, which goes down to 65%. Same thing for the running costs, down to 65%. For the chip process, I'm making a similar assumption, but I'm saying, okay, it takes 2 times as long to process a 6 inch wafer compared to 2 inch. And then with a larger area, twice as long, we have 4.5 times the throughput. So one last game here is looking at this for 8 inch. And we have a capacity advantage. We moved to 8 inch already of 43% in this reactor. If we take edge exclusion into account, it's a 74% advantage. So the cost goes down to about 58%. Also the cost of consumables. And for the chip process, if it takes 2.5 times longer to process an 8 inch wafer, we still have a throughput advantage of 6.4 times. So very, very clear advantage of larger wafers. For the next subject, let me talk about yield. And I'm going to show you a few examples. This is the 69 by 2 inch configuration, the showerhead system, Prior's 2L showerhead system. And we have at 460 nanometer wavelength, we have an on-wafer standard deviation below 1 nanometer and a wafer-to-wafer distribution max min of about 3 nanometers. For 4 inch, we have 16 4 inch wafers in here, similar wavelength, on wafer a little bit more than 1 nanometer, and wafer to wafer actually even less, about 2 nanometer max min. But why am I showing you this? Well, because it goes into yield. The distribution of the chip wavelengths is basically a convolution of the on-wafer and wafer-to-wafer distributions, and it's a fairly Gaussian type curve, and the yield will be determined when we define the bin size. So once we define the bin, we can see how many of those chips are usable and how many are not. And the yield depends very much on how narrow this curve is and how wide the bin is. And we can see this on the next diagram. This is the data I've shown you before, goes into this, and we can see the yield of the bin size. And about 5 nanometer, at a 5 nanometer bin, we have more than 90% yield in this reactor. If we look at several consecutive runs here, we can see actually the yield of each run is below 90%. Why is that? I just showed you 90%, more than 90%. Well, this is because every run, from run to run, there can be a small deviation in the wavelength, or the center of gravity shifts. Some manufacturers call it the hit rate. And it's very simple. If this curve is shifted a little bit while the bin window is the same, then we're gaining some chips here, but we're losing more here, and the yield goes down. So now I'd like to show you how we address this issue, and it is basically done with temperature control. Why temperature? Well, the temperature is so important because only 1 degree centigrade makes a difference of about 1.5 or even 2 nanometers in the wavelength. And to control the wavelength precisely within the run and run to run, we need to pay special attention to the temperature. Okay, so what we're doing here in the shower head system is measuring the temperature of the surface, and we're feeding this back into the heater, and then this controls the radial distribution over the susceptor, and also it controls the temperature from run to run. So here we can see a temperature mapping of the whole susceptor, and this is about 1.3 degrees temperature distribution. And the 1.3 degrees, remember I said about 1.5 nanometer per degree, translates into 2.1 nanometer distribution. This is actually the data that I've just shown you a few slides ago. So it helps a lot in controlling the yield. Now, run to run, we can adjust, let the system adjust automatically the wavelength. And if we now look at the run to run data, we can see that we are very close to 90%. Always high yield. It's because run to run we have about 0.2 degrees centigrade, and that translates into about 0.3 nanometers. Okay, we have a similar tool for the planetary reactor, and actually we are again measuring the temperature from the top, and then we're controlling actually the flow of the satellites. The satellites are propelled by a gas to rotate, and the amount of gas determines the flying height of this panzer, and therefore its temperature. So it will allow us to individually control the flow for every satellite, and therefore adjust the temperature for every wafer. And we can see here, without temperature control, we have a variation. Each point represents one 4-inch wafer. We have a variation of about plus minus 3 nanometers, or 3.7 degrees centigrade, which translates into plus minus 3 nanometers. If we let the system control the temperature, it goes down to almost 0 with a wafer-to-wafer variation of plus minus 0.25 nanometers. Okay, last subject is automation. And to motivate this, I have here a picture of the first transistor ever made. And this morning we saw a slide on the three inventors of the transistor, right? Fits well in. And here is a actual picture of a transistor production in the 1950s. That's what it looked like by then. But today, a silicon fab looks very different. This is more what it looks like now. We have here the front end, and behind these walls, this is where the actual equipment is running, automated on its own. What about LED industry? Well, I think this is where it's going as well, mid-term to long-term. And but we have to be aware we can actually address basically the 10% of the cost here only. But the most important reason for automation is actually it reduces the human factor, which then itself again goes into the yield. So let me show what we're doing here. Here we have a shower head system automated. It's actually can deposit on a 300 millimeter wafer. This is not used for LEDs, used for other applications. Here is a planetary system with a transfer module or a handler, and we're going to look at that a little bit more in detail. First, we look at the operator interface. We see here it's still a glove box and a load port and a touch screen here to operate this front end. Now we look inside of this user interface, and we can see here the wafer is put on the satellite, and then we slide the satellite into a so-called magazine. That's where we keep the satellites and wafers, and that's where they're going to get picked up by the handler. So in the next picture, we look into the transfer module, and we can see how the robot picks up the wafer and satellite, and then puts it into the reactor. So now we look into the reactor, and we can see how the robot brings the wafer into the reactor and puts it down. So the next natural thing is, because this handler is not a very busy guy, an LED process takes 7 hours or so, so this guy is usually sleeping. That is why we can actually let it operate 2 reactors, and that's what we see here. Here is a picture of the system in our laboratory, and here we see a picture from another perspective. And this concludes my presentation for today. Thank you.
Thank you for your speech.